I want to do this as a separate video. The calculations get a little bit long, but it's important to understand the problem and how and why it works and how to match things up at the end. So let's give ourselves some time to do this. Remember the good old volume of a box problem from Calc 1? You had a sheet of cardboard, you folded up the edges, and you wanted to find the largest possible box with no lid. And then you had other versions of it, right? You wanted to minimize the cost of a can. You wanted to maximize the volume of a can or some other cylinder within a certain set of parameters. So now we're going to do something similar. This time, what if I had a sheet of cardboard and I knew the area of the cardboard sheet, but nothing about the dimensions or the shape? How could you find the maximum volume? So here's my question. I've got a box with no lid. It's going to be made from 2 square meters of cardboard. So I don't know that like one side is 10 and the other side is 8. I just know I have a box with no lid and how many square meters of cardboard I have. Find the dimension of the box with the largest volume. My hint down the bottom here was to start by calling x and y the dimensions of the base and h the height. So we're going to attempt to draw a cube here. Well, it's not really a cube, it's a rectangular prism. All right, so we connect the dots here and here. Actually, we connect that one. It's the outside. There we go. All right, so x and y are going to be the dimensions of the base, and h is going to be the height. Now, I said with no lid, right? Box with no lid. So with no lid, that leaves us 5 surfaces. The surface area, then, is what? It's the face in front of you, which is x times h, but then there's also another x times h in the back. All right, so this is front and back. Now let's look at the left and right side. The left and the right side are y across and h up. So there's 2 of them. And then there's one base. The one base has dimensions x, y. What do we know? We know that there's 2 square meters of cardboard. That 2 square meters of cardboard is going to become the surface area. So that must mean that the surface area is equal to 2. And we're trying to maximize the volume. Odd thing, we don't seem to have a formula for volume. How do you find the volume of a prism? Well, the volume is length times width times height. So volume for a prism, length times width times height. Well, in this case, the height is just h, so let's call the height h. It would be helpful then if I could solve for h in terms of the other variables. So let's take my surface area formula and work that around so I can solve it for h. So maybe I'll move the xy over to the other side. So 2 minus xy equals 2xh plus 2yh. Factor in h out of the right-hand side and divide through. So 2 minus xy, I'm going to divide both sides by 2x plus 2y. And I'll end up with a formula for the height as 2 minus xy over 2x plus 2y. Great. Now what? Well, the main formula that I have is the volume. Whatever we're trying to maximize or minimize, remember in Calc 1, everything you were trying to maximize or minimize went back into that main volume formula. Well, the same thing happens here. So volume equals x times y times 2 minus xy over 2x plus 2y. Do a little distributing. So you'll end up with a 2xy minus x squared y squared over 2 times x plus y. If we're trying to find maxes and mins, then what we need are partial derivatives. This is going to be sort of a long process. Hang in there, follow along, see if we get the same answer. First of all, I can write this, by the way, as 2xy minus x squared y squared over x plus y times a half. Which means I'll just pull the half out of the whole partial derivative with respect to x and just worry about the quotient rule from there. So it's going to be bottom derive the top. So bottom is x plus y. Derive the top is going to be 2x. Now I'm deriving with respect to x, so actually it's going to be 2y. Because if I derive that first term with respect to x, I get a 2y. So 2y, and then derive the second term with respect to x, I get a 2xy squared because the y squared is treated as a constant. So bottom derive the top minus top, so I just get 2xy minus x squared y squared. Derive the bottom. Well, when I derive the bottom with respect to x, I just get 1 all over, we'll carry the 2 along for the ride, x plus y squared. Clean up the top a little bit. If I clean up the top, I'm going to end up with a 2xy plus 2, or minus 2 x squared y squared, and then plus a 2y squared minus 2xy to the third. And then the second term will give me a minus 2xy. Oh, all right, minus 2xy. And this thing in the middle is a minus sign. And so minus minus will make a plus x squared y squared. So plus x squared y squared. This gives me nothing here. It gives me a negative x squared y squared plus 2y squared minus 2xy to the third. Simplify that. Pull out a y squared, and you'll end up with a y squared times 2 minus x squared, I just switched the order, minus 2xy over 2x plus y squared. That's the partial derivative of v with respect to x. Now do the partial v with respect to y. You're going to have to rely on what you've written down because we've long ago passed that point where it's on my screen. The partial derivative with respect to y is going to be bottom derive the top. So the bottom is x plus y times 2x minus 2x squared y minus top derive the bottom. So the top is just 2xy minus x squared y squared. Derive the bottom, I'll just get 1. When you go to work your way through and clean this up, what you end up with is something very similar to what you had on the top. You end up with the partial derivative with respect to y as being able to pull out an x squared, and you're left with 2 minus x squared minus 2xy over 2 times x plus y squared. Now, compare the red partial up on the top. Here, I think this. Who knew there were glitter pens on this program? There's one up there, and then the other partial derivative that you have is the partial down there. Look at the difference between them. The only difference is that here I've got an x squared and an x squared. Here I've got a y squared and an x squared. What that must mean is that the two things are the same whenever either x is equal to y or x is equal to negative y. Well, it doesn't make sense that x is equal to negative y. That would make it undefined on the bottom. So it must be true that the things are the same whenever x is equal to y. Great. What does that mean? Well, if I took each of these partials and set them equal to 0, right? Let's take the partial derivative with respect to x and set it equal to 0. Partial with respect to x is y squared times 2 minus x squared minus 2xy over 2 times x plus y squared. Set that equal to 0. Well, that's only going to equal 0 in two places. Either where y squared is equal to 0 or when what's in the parentheses is equal to 0. So we already noticed that the only difference happens when x and y are the same. So our interesting points happen either when y is equal to 0 or x is equal to 0, right? When they're both equal to 0, that could be one interesting point. The other point happens when x is equal to y. So let's go into the set of parentheses, because you realize if I go back to x being 0 and y being 0, then I don't really have a box. So let's go back to the places where x and y are the same. So I'm going to sub x equals y into here. And I'll end up with a 2 minus x squared minus 2 times x equals 0. And now I'm getting somewhere because I'm into one variable. So I end up with 2 minus x squared minus 2x squared. So that's 2 minus 3x squared equals 0. 3x squared must be 2. Carry this across, that'll give me an x squared equals 2/3. So x equals, well, technically plus minus the square root of 2/3. But I'm not going to include the negative because if I do, I'm saying there's a negative side length to my box. Hit the top and bottom with the square root of 3, and I end up with x equals the square root of 6 over 3. Well, if that's x, that's also y, because both of them then turn out to be square root of 6 over 3. What's the height? All right, so x and y are both square root of 6 over 3. What is the height? Remember way back at the beginning, I'm going to flip my paper over so I can pull the function up here. Way back at the beginning of this problem, we said height was 2 minus xy over 2x plus 2y. And now we have to throw in those values we got for x and y, and we'll find the height. So I end up with 2 minus root 6 over 3, root 6 over 3 over 2 times root 6 over 3 plus root 6 over 3. Okay, so that gives me 2 minus 6/9, which is 2/3. On the bottom, I'll end up with a 2 square root of 6 over 3. Multiply it by 2, and I get a 4 square root of 6 over 3. If I keep this process going, and there's not really much more to the process, but you will end up with a height of square root of 6 over 6. All right, so the dimensions of of x and y being the same will maximize the volume. So the maximum happens when x and y are both square root of 6 over 3, and when the height is square root of 6 over 6. And if you would like to find the volume, take length times width times height, and you'll get the volume. Relatively simple calculation. But that's it. One long optimization problem. I think there's one in the lab that's kind of like this, so I wanted to run through one first.